All right, guys, back to me. You should have had plenty of time to draw a reaction coordinate. If you were a little behind, then you need to jump on board. Let's go. So if you did not get your web quest checked yesterday, it should be in the box at this point. And then you're drawing an exothermic reaction coordinate. Everybody draw that in the air for me. All right, I see a lot of us are starting high. There's the little hump, and then we go low, right? Now, I do want you to quantify it. That's why I've given you numbers. That means I want some numbers on an axis. So I'm going to ask for some help as we go. So Gwen, give me the x-axis on the graph. Time. Alicia, give me the y-axis on the graph. Kilojoules. Good. That's one version. You could also put PE, which means potential energy, which is just an energy unit. If you have not started drawing this, you need to begin now. At this point, if you're rifling through papers, you need to begin now. Let's go. So I already saw the big kind of curvature you guys expressed like this. Okay, but I want some numbers on here. So Matt, give me a number I can put right here for the beginning where the reactant's energy is. It doesn't matter. It's just a number. Can you give me a number, sir?
Any number?
Yes.
50.
50. All right. So 50 kilojoules is where we're starting, apparently. That was Mac's choice. And then it says that the energy release was 25 kilojoules. So Hunter, how would I label the area that's correlating with the products down here? Why 25? Right, because we have to have 25 kilojoules of energy released, so there has to be a difference of 25. Well, that just worked out. 50 minus 25 is 25. So this difference here, please do not get up again. You guys had a chance. Move on. Sit with me and do warm-up. Thank you. So this correlates with the energy of the product, or the products, which is 25 kilojoules. All right. So we had a difference between reactants products of 25. There's another way to label that, and you can put like a little arrow scheme like this, and that's going to be called what for us? No, that's not EA.
What's the
95.
Oh, that's not.
Hold on, we're going to get to EA in a second. What is this difference in energy of reactants and products? H. Good. Delta H. Right, so this is also called heat of reaction. That's one way to call it. What's the E word for that? Good. Enthalpy. You know there's like 3 names for everything in chemistry, sorry. So the enthalpy of reaction is what in our case? So I'm going to put a negative on that because it's being released. So this is negative 25 kilojoules. So the difference in energy is just the difference between the reactant energy and the product energy. Are we clear on how to get energy of reaction? Okay, so if a reaction, it can't occur just always by itself. It has to have a set amount of energy that's jump starting it. That we said was what here? 95 kilojoules, right? So the activation energy is 95 kilojoules. So everybody, where I'm going to label some pieces here, A, B, and C. What, the difference between what 2 letters gives me activation? A and B. Because the difference between A and C was what? Was the heat of reaction, or the 25 kilojoules. So the difference between A and B, this peak right here, that is EA. That is activation energy, which in this case is how much? 95. That's just because I told you guys it was 95 according to the reaction. Okay, so everything's been labeled. We're good to go. And second, or third, or whatever, I've asked for you to provide information about what a catalyst would do to this. So everybody, what would be slightly different here?
The hump would be lower.
The hump would be lower, okay? So sketch that on yours. Okay, so you guys said lower, so it's going to be like here. So for the definition, I'm going to maybe bolden this up for us so we can see this. The definition of a catalyst, and if you don't remember it, make sure you write this piece down, is that it, well actually you guys tell me, what factors do you know about a catalyst? Okay, so that's our biology definition, is it speeds up a reaction. That just says, hey, it moves faster, the rate for the reaction is faster, but tell me more. Okay, by lowering EA. Okay, so it's lowering the activation energy. So now instead of being 95, what would be a good number for this little peak right here? 2 kilojoules it is. Okay. So we have a small amount of energy that's required. So that reaction is going to happen quite fast because all those collisions will meet that 2 kilojoules of energy it requires. EA is activation energy. Energy of activation is what the EA stands for. So it speeds up reaction by lowering activation energy. And then I'm going to add 2 more pieces here. It alters the reaction pathway. And I know that this seems kind of weird to say, but the way we express the different pathway is that the first one, the red one, was a big peak. The green one was the altered pathway. It starts at the same place, it ends at the same place, but the path taken is different. That's what that means. And then lastly, is it consumed? Is it used up in a reaction? No, that's a definition or a term or a characteristic about catalyst that you should know. So it's not used up. So what are different examples of catalysts in your body? Enzymes, right? We talked about some of them in our food. Actually, some of you guys talked about really good enzymes in your food diary thing. So you guys talked about amylase, which is in your saliva. It breaks down starches. Protease breaks down proteins. Lipases break down fats and lipids. So those are just some, but all those enzymes are happening to be in your body at all times. It would be horrible to like eat a nibble of a sandwich and the amylase breaks down that starch, and then immediately amylase, the enzyme, aka catalyst, is just destroyed. Your body would have to be pumping out enzymes like non-stop every minute. Your body wouldn't be able to do that. So therefore, catalysts and enzymes are not consumed. Your body can reuse them and reuse them and reuse them and reuse them until they're like just so kind of degraded that they have to kind of kick them out, break them down, and dispose of them. But your body will use those all day for maybe for years in some cases, just because it's so wasteful to kind of keep, you know, breaking them down and building them back up, breaking them down. So that's why we say they're not used up, because our bodies couldn't handle that. Okay, we good here? Okay, so you have stuff on your desk for me. You have blank paper, you have reference table, you have calculator. Spread out so you're not sitting right next to somebody. You sit on the lap. Just close to each other. I'll do it. Alright, you can sit diagonal from someone, but you cannot sit right next to someone. Everybody stand this because I told you about it before break.
Are you moving or what? Or you want me to? I will.
Where's she over? Alright, you have 10 seconds, find a seat. 10, 9, 8, 7, 6,
Alright, I'm actually doing
5, 4, writing quiz. 3, 2, 1. Okay, so you found a seat, thank you. And then please don't write on this paper. You have your entire blank paper to do work and scratch work on. Everybody has a reference table, correct? Okay, on the back of your reference table, please find the equation. You see the pH equation. Yes or no? Yes. The answer should be yes. You can't function right now without a reference table. I want you to right now very clearly write 1 through 15 on the upper left-hand side of your paper. 1 through 15. I want like a little answer key at the top because I'm not hunting for your work answers. Your work should be somewhat organized, so if I wanted to go through and see mistakes, I could find them if I needed to. That's the way this works.
Yeah, I'm sure.
Thank you. So at this point, you should have the quiz. You're making a little answer key at the top for me, and you have all the extra space in your sheet. Okay. Okay, so we know that these three things must occur for the reaction to even like pretend to happen. If they don't collide, the reactants won't allow products to form. It's simple as that. The one thing we kept saying yesterday was like enough energy, enough energy, enough energy. But now we know what we are comparing that to. We're saying it has to have enough energy to meet what requirement? The activation energy. And is that the same for every reaction? No, like this will differ based on the reaction that's occurring. And so the example that was in the web quest was, using baseball as an example. And they had some that were really efficient collisions and some that were not so efficient collisions. Which ones were the crappy collisions? The foul ball? All of them? Okay, so the foul ball was not an efficient collision because it didn't collide properly or the proper orientation. The one that like skinned the ball, kind of not a whiff, but it just flew off the back of the bat, is not a proper orientation. What would be an example with baseball that would be having sufficient energy? A home run, right? So like gone. The ball would have to clear the backfield. So outfield, backfield. So we'd have to have enough energy for it to go out of the field, and that would be an efficient collision. So what we're talking about with these graphs now are that different reactions have different activation energy. Who would be easier to achieve, an exothermic reaction or an endothermic reaction? Exo, look how little this activation energy is comparatively. Endothermic reactions, do you remember that back when we talked about like spontaneous reactions, which ones were favorable, exothermic or endothermic? Exo, when you with me? Okay, so exothermic were favorable, where endothermic, we gave the frowny face, not favorable. And that's because look how hard it is to achieve that amount of energy. It's just like, it's impossible. That's the reason behind it. And we kept saying that, but now you know why. Let me skip that for a minute. Okay, so you have a couple minutes. Talk to your group mates about these questions. Go. Use your big words. Alright, back to me. 3, 2, 1. I'm gonna get some help here, okay? Alicia, lowering the concentration of the reactants will decrease the reaction rate. Why?
Because when you see the starting with the baseball, if you would lower the speed of the baseball coming towards the bat, it would hit the ground before it would hit the bat, so it would be able to.
See, that's speed. Nothing here says anything about like fast, how fast something is. So I'm gonna come back to you because I like your idea with kinetic energy in just a second, okay? Ayushi. So we can't talk about speed. This has nothing to do with temperature at all, right, Glenn?
Is it that the reactants have more things to get around to meet the other reactants?
More or less? Look, this is talking about decreasing rate.
More. It has more other things. Like the reactant.
Okay, so if you lower the concentration, but that means there's nothing else there.
So it's just volume, there's less of it.
There's less of it, okay? So less of it means... Alright, hold on. Raise your hand if you can put this into, like, simplest terms possible. Parker.
Less particles.
Lower concentration will lower the number of particles. Okay, I'm with you.
And it will decrease the amount of collisions.
That's it. That is it. You guys are like thinking above your pay grade right now. Let's get back to where we're comfortable. If you have less stuff, they won't collide as often. If you don't collide as often, you don't have the reaction's not occurring. That means the rate of the reaction is really slow. Yes, ma'am.
Why not say volume instead of the concentration. Doesn't that imply there's something else?
Well, maybe implies it's like surrounded by water.
Okay.
So that's why I knew you were thinking about other stuff, but the other stuff is not hindering the reaction necessarily. Or sorry, the other stuff is not allowing it to react. It's actually hindering the reaction, because if reactant A is surrounded by water, it can't get to reactant B very well. But if there's a lot of reactant A and a lot of reactant B, they're going to bump into each other like that. So if there's less of them, that means there's lesser particles, which means they're not going to meet with each other. That means they're not going to react. So you were right to say there's other stuff, but missing the point. Okay, gases react more quickly than solids. What you got, Allison? So when you say they move more quickly, that's exactly what I have here. Give me some more. Yeah? Give me the reason why moving quickly would force a reaction to occur. More often. Okay, so there's two parts to this. Moving quickly means that you increase your number of collisions because you move fast, right? And yeah, we're reviewing. Yes. So this group over here, tell me the other piece of it.
They because they're not all together, they would
So they're not all together. So and both of you guys were talking about this is all clumped together, this is spread out. So that has something to do with it too. But there's one more piece about how the fast moving particles does something special. Ethan?
It allows it to have the activation energy.
Okay, so you're saying energy of collision is greater or lesser? Greater, right? So gases moving fast means that they really smack each other, right? So this has a higher collision energy, higher energy of collision. That just means that when they collide with a lot of energy, hey, I'm probably going to meet activation energy. Solids, you're right, they're moving slow, they're packed close together, they may not collide with enough energy, so they may not react all the way. So that has two parts to it because it deals with energy and speeds and temperature. Okay, so kind of similar story. A decrease in temperature will cause a decrease in reaction rate. What you got, Madeline?
Well, it's kind of like the same thing with just some good temperatures lower.
Okay, I'm going to use one word instead of slower. I'm going to say lower kinetic energy. Okay, which means that they move slower. Okay, so they're moving slower. Do they hit frequently? No, so decreased frequency of collision, and everybody else, not only does the frequency of collision decrease, but what also decreases? The collision energy, good. So decreases energy of collision. Okay, whew. We're getting there, but yes, we are reviewing. These are the 5, related to the 5 ways of speed of reaction, but we're trying to manipulate how we talk about them. List 3 ways that a reaction rate can generally be increased. Hunter, tell me one. Shush. I want one person to answer, and it's the person I asked for. Thanks, Hunter. Well, I can't just give it more energy. What would I do to give it more energy? Increase temperature. Okay. Give me another, Emery. It's okay if you repeat some of the other things we've talked about too.
lower the concentration.
Well, we want to increase, right? So I want more collisions.
Oh.
So instead of lower the concentration, I want to increase the concentration. Good. Josh? Introduce a catalyst. Good. Will?
Lower the concentration.
No, that would slow it down, right? So we said increase concentration, brackets mean concentration, right? Molarity. Increasing concentration means more stuff will collide. That would increase the rate. Give me another way to increase the rate.
Decrease volume.
Decrease volume, because that means they're compact, closer together, so they're required to collide essentially at that point. Nathan, you got one? There's one more. There's one more. Anybody? Matt? How would I increase the surface area? Make it a smaller particle size, powder it. Okay, and then we all should be able to say in a brief term how to speed up a reaction with a catalyst. What does it do? It lowers the activation energy. Okay. All right, so do we feel okay with rates like speeding up or slowing down reactions? Okay, you have to be able to describe it. It's not like, oh, I just know the 5 factors, which are these. Being able to describe it helps a lot. All right, so we're going to draw a quick graph to understand how the rate of reaction can be expressed graphically. Write this down first. Okay, this is like a fraction right here. So we'll switch in a second. Okay, so just like you ride or drive to school, we talk about how things change per time. So, Courtney, how fast did you travel to school this morning? How much? 45 in a school zone? Oh my gosh. Okay, so 45 miles an hour. So if she had a full hour, she would travel a whole 45 miles. But we're not talking about physics right now. We're talking about chemistry. So in physics, we talk about distance versus time. But in chemistry, we don't like have particles moving in distance, right? We have them in a test tube and we're looking at them. That's it. So we look at them and we try to measure something about them. If you had like a colorful reactant and it was pink and it changed from hot pink to light pink to baby pink to no pink, we could see that color change over time. If we knew that reactant was pink, we could then look at how the quantity of the reactant changed over time. So we don't measure distances in chemistry, we measure amount of reactants. So amount, though, is not given to us in just any old amount. What's our favorite unit? Moles, right. Many times this is going to be looking for moles or even molarity as it changes over time. What's another way of saying just molarity? Like really generic? No, concentration. Molality is something totally different. Okay. So we're looking at how concentration changes over time. Or if we had a colorful product species, we would be looking at color changes of products, and we could see it was clear, and it was light purple, and it was dark purple, and we could see how that changed over time. So this is described, I'm going to write this a little simpler, change in concentration over change in time. What does bracket mean again? Concentration in molarity. So using that information, change in concentration over change in time, let's draw a graph. Go ahead and sketch first. You don't have to have all the numbers on it. Just give me a sketch. What's the y-axis? Concentration. And what's the x-axis? Time. Huh. Where did we just see that?
The black thing.
Concentration versus time. Concentration versus time. Sketch that first and just label where you can. All right, so you have like 4 lines to draw. Good job, guys. All right. So, what we should realize is that the downward sloping line is representing what here? Reactants. Good. So, what's happening to reactants over the course of this reaction? They start up here at 0.1 molar, and where do they go? They decrease, decrease, decrease. But look at the slope. It's kind of steady there. And then what happens to the slope as they go more? It's decreasing in slope. It's decreasing in slope, it's decreasing in slope, it's decreasing, and eventually it's going to level out to 0 slope. Okay, so let's think about that, what that means. Slope here, what in general, what is slope? Huh? Change in y over change in x. Okay, so it's like y2 minus y1 over x2 minus x1. Is this ringing a bell? Okay, slope, we know what slope is. So we're looking at change in y. Well, what's y? Change in concentration. And what's x? Change in time. Where did we just see that? It's the definition of what? It's the definition of rate. Good. So the slope is the rate. Good. The slope is the rate because we see that it's changing concentration over changing time. The slope is the rate. So what happens to the slope over time here? It starts off pretty steep and then it starts to level off, which means decrease, decrease, decrease. So is the reaction getting faster or slower over time? Slower over time, because guess what? Yeah, bunch of reactants. It's happening real fast, a lot of collisions. And then what happens like here? So we say lots of collisions. And then here, some collisions, okay? And then here, I'm gonna say few, like very, like they could still be colliding and reacting, but it's very few collisions. And it's just because, hey, I've only got like 0.01. This is up here is like 0.08. So we can see how the concentration does impact rate over time. Now what's the other graph, or what's the other line? Products. Why are they starting at 0? Well, at time 0 before the reaction occurs, I have all reactants and no products. But as those reactants react, what are they producing? Products. And as those reactants continue to react, they're making more products and more products and more products. But as the reactants slow down in their reaction, what's happening to products? Slowing down in how much they're produced, right? Slowing down in how much they're produced or how fast they're produced. So this mimics the same thing that's happening here. Okay, this correlates. Do you see the correlation sum? Yes? Okay, what is slope representing one more time? Rate, because it's whatever what? Concentration over time. Good. So we'll look at these graphs a little bit more in depth later. Before I move on, write the reaction for this graph. Write the reaction for this graph. You have to look a little closer. Now look at the details given that weren't given on the other one. All right, Sheeta, get me started. H2. Okay, so she sees a reactant given here. Get me continued. Serena. Plus I2. Good. So these were the two reactants provided. Ashton's on here. Courtney, finish. Yields to HI. And she saw that because of the product given here. Okay, is this balanced? No. What do I need? 2 in front of HI. Okay. Can you see how that graph looks a little wonky? Is it like exactly identical? No. Which one is the steeper slope? So blue or red? Blue, which is the product. Good. So why do you think it has a really steep slope right here? It's making 2 times the amount of products than the individual reactants. 1:1 to 2 ratio. So do you see this is almost twice as steep as the red? You should be able to tell like there's a reaction and there's a different number of products and reactants reacting. As long as you can see that, we're good. All right, so keep going. We're going to do our lab, so hold up. The last thing I need you to write is this term. We've been saying, oh yeah, these collisions are occurring, but there's a word that qualifies that it's a good collision. The word is effective. It's an effective collision, but we've never really written that down or said it. So we say the reaction rate, like how fast the reaction is occurring, is equivalent to not just, hey, like they're colliding, like they could collide and still be a foul ball, right? They could still collide, just not collide correctly. So we like to say that it's proportional to the number of effective collisions. What do I need for it to be an effective collision one more time? Langston, give me one thing it needs for it to be effective. Right? I'm going to use the word orientation for that. So correct orientation. And the other, Amina? That's what we spoke of at the very beginning. It has to, when it collides, it must collide with the correct orientation and speed, which we wanted, so instead of saying speed, we'll say energy, right? Meeting activation energy. Okay, and then the last thing is that we kind of ignored, like, sometimes reactions can be very, very complex, because we kind of just said, hey, it's good for reaction if I increase concentration or whatever. But sometimes the nature of the complexity of reactants and products can affect how fast a reaction occurs. So if I have like glucose, C6H5O6. This is not quite glucose. I'm giving you a complex drawing though. Let's put some methyl groups off the side. Okay, so that looks pretty complex. It's got a bunch of bonds in it, right? So do you think it'd be easier to make that or to make that? Probably water, right? 2 bonds, we can make that pretty easy. To make glucose would be pretty challenging, so a reaction can slow down based on the complexity of the reactants and products. Does that kind of make sense though? Okay, cool. Pull out a piece of paper, call it iodine clock reaction.
The kind of hard or like
This last one. It's good.
easy and your eyes are like 5.
It's a nice lab. Let me finish explaining the lab and then we can talk more if you would like to. Iodine clock reaction. Right, if you can turn and talk to the person next to you about like 30 seconds to remember how iodine and starch react.
Who do you want to be? It is a lab.
First question. I'm gonna wait on. Alright, back to me. And you're gonna say the color in 3, 2, 1, go.
Blue.
Bluish, purplish, blackish. Good job. Okay. So it turns a blue-black color. Okay, so we know that that's going to indicate to us that a reaction has occurred. Yes? Hi. Thank you. Oh, thank you. I people like. Ooh, how much is this? How much is this t-shirt? It was 15. Thanks. Okay. So back. Sorry. Good. Gotta pay people. So we know that with this reaction is going to occur. A plus B is going to yield C. C is this black-blue color. That's how we know the reaction has actually processed. So Gwen, what do I need for this reaction? Materials. Okay, you're gonna use your phone. I need some sort of beaker, right? Small beakers are fine, big beakers are fine. I'm gonna go and portion out solution A and B to you in small beakers, and then you guys can proceed from there. You do need a couple test tubes. You need some grad stills. You're gonna use what you have at your station just because there's a lot of materials needed for this particular lab. If you don't remember how to set up a hot plate, the hot plate moves 10 degrees every time you turn it by 1 on the little turn knob. So your hot plate looks kind of like this. 2 knobs, right? Don't need the stir knob, you need the temperature one. So for every 1 on there, it's going to be 10 degrees. On the procedure, it says don't go above 50 degrees Celsius. I would turn that thing to the 3 and let it rip. Let it get to 30 degrees and then you can move on. Don't go to 50. Don't even go close to 50 because your reaction will kind of get wonky. The hot plate, you'll put a beaker on top with water about halfway up, and then you'll insert your test tubes in there like it says to do in the lab. For an ice bath, all you do is get a beaker, fill it about halfway with water, and you'll put a little bit of ice in it. That's an ice bath. Do you remember how to do these? Okay, cool. And then lastly, what I'm going to tell you is that your solutions, you don't need very much of them. Solution A has iodine. Iodate is IO3, which has iodine in it, which is why we were talking about iodine at first. And solution B is acidified starch solution. Don't waft it, don't smell it. It's bringing nose hairs out, okay? It's harsh. But acidified starch solution kind of has this blurry appearance. I'm not labeling beakers for you, so remember, be blurry, okay? And as it states in the lab, you're going to have a hot trial and a cold trial. Your last, the third trial will just be the first one that you took, which would be at room temperature, which is about 25 degrees Celsius. So I've given you a lot of information. Any questions right now? You can ask me stuff in the lab. We're going to have 9 lab groups, so listen so you know which lab group you are. Write it down. You got to look at me there, okay? Olivia, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, 5, 7. Wait. 8, 9. 1, 2, 3, 4, 5. You guys need to make that finish, okay? So go to your lab group. 1 through 9. Yeah, I actually do. Where are you? 1 is over in the corner. 2 is in front. 3 is in the back. 4 is in the very back. 5 is in the middle back. 6 is up here on the side. 8 and 9. Alright, so let me tell you what I need for my groups. Alright, so one, everybody hold a flat sheet that should be on the desk already. So if you don't have your hand up, come grab one now. I have extras right here. If you don't have a flat sheet, let's go. More? Okay, cool. So I've got 3 more for anybody who doesn't want to share. So 4 more. I'll leave those here. Second, you're going to send, listen, you're going to send one person in just a moment when I say go. Come grab a loud bottle. And a second person with 2 beakers. And I will give you some solution A and solution B. Go. Yeah, small for only 40 milliliters. Hey, Matt, go to If I don't give you enough, you can come back more later. Alright, any more solutions? Alright, so let me give you a tip here, okay? Listen. So you have a data chart, you're drawing trials 1 through 4 from the back of the lab sheet. I have more lab sheets if you need a second one, I can get that to you in a second. 2, one person probably should be in charge of measuring out A, another person in charge of measuring out B, another person in charge of measuring out water. Yes, the first trial requires 0 milliliters of water, but after that, you'll be using water. I have pipettes there for you. I would wash those babies out because you don't know if it was A or B earlier. So get a little beaker of water and get some water so you can rinse things out. And then lastly, I have a big old waste beaker right here. You see the waste beaker? It's full. So I'm going to put another one out, and at the end of the lab, you can come and bring your waste to me. But at the point that you are at right now, you probably have your own waste beaker at your table to share. Any questions right now? Get moving. Okay.
Dolphins on deck. Let's go.